Founded in 1885, Stanford University is located on 8,000 acres in the heart of Silicon Valley and is home to over 1,000 buildings. A large research campus such as this requires a substantial amount of energy to operate, resulting in significant greenhouse gas emissions and cost, which makes adept management of resources a priority. Since the 1980s, Stanford has employed best practices to minimize the cost and environmental impact of its operations. The campus has employed energy metering in all its facilities, used efficient natural gas-fired cogeneration for its energy supply, retrofitted buildings with efficient systems, implemented stringent building standards, invested in renewable power, conserved water, and reduced automobile commute emissions to 1990 levels. In 2008, facing continued growth and an aging energy system, Stanford embarked on an in-depth analysis of its long-range energy needs. The goal was to develop a progressive new energy system that would be economical, flexible enough to adapt to future changes in technology, and demonstrate leadership by example in environmental sustainability. This planning effort included a broad search for innovation from faculty, staff, students, and industry, development of detailed engineering and financial models, and extensive peer reviews. Completed in 2009, the key components of Stanford's energy and climate plan are high-efficiency standards for new buildings, continued efficiency improvements in existing buildings, and a cutting-edge energy supply system known as the Stanford Energy System Innovations project, or SESI, which we feature in this presentation. SESI represents a significant transformation of the university from 100% fossil fuel-based cogeneration to a more efficient electric heat recovery system, powered by a diverse mix of conventional and renewable energy sources. In late 2011, Stanford's Board of Trustees approved the $438 million investment in SESI to meet the university's energy needs through 2050. Upon commissioning in 2015, this new system will cut campus greenhouse gas emissions by 50% and reduce campus water use by 18%, while providing the lowest energy cost of the options studied, including cogeneration. Through a detailed review of campus energy use during the planning process, Stanford identified a significant simultaneous need for both heating and cooling in its buildings throughout the year. In a typical large university building, different rooms require different temperatures depending on what kind of equipment and activities are taking place. For example, labs and IT rooms with heat-generating equipment require more cooling than office spaces, so the main air supply to the building must be cooler than the air supply to the office spaces. Consequently, the air to the office spaces must then be warmed locally. This local warming, known as the reheat process, is accomplished by the building hot water hydronic system using heat currently provided by the campus steam loop. At Stanford, the real-time overlap of heat being collected from the campus by the chilled water loop and heat being delivered to the campus by the steam loop occurs 70% of the time. This substantial overlap presents the opportunity for heat recovery, using the waste heat collected by the chilled water system to meet simultaneous heating demands instead of discarding it. SESI will incorporate heat recovery as a key feature for meeting Stanford's long-term energy needs. A series of animations will now show how heat recovery is a more efficient source of energy for Stanford with distinct environmental benefits. In cogeneration, natural gas is used to produce electricity and steam for building power and heat. Some of this electricity and steam is also used to make chilled water to cool the buildings. Electricity, steam, and chilled water from the central energy facility are transported across campus to buildings via underground cables and steam pipelines, and very hot water, known as condensate, and chilled water are returned back to the central energy facility for reprocessing. At this facility, waste heat from the buildings collected by the chilled water system is discharged into the atmosphere via evaporative cooling towers. Most of the university's energy is currently supplied by the cogeneration plant in this way. A close-up shows how steam and chilled water currently meet the simultaneous demand for heating and cooling for campus buildings, creating the opportunity for heat recovery. First, we show the steam loop with the red lines. Steam from the central energy facility enters the building and through heat exchangers produces both warm air for space conditioning and hot water for restrooms, kitchens, and laboratories. Afterwards, the steam changes into condensate and returns to the central energy facility to be reheated back into steam and then sent out to buildings again. Now we show the chilled water loop with the blue lines, which can also be thought of as a process of collecting waste heat. Chilled water enters the building and through a different heat exchanger provides cold air to cool the building. After collecting waste heat, the chilled water is then piped back to the central energy facility for recooling. In the new heat recovery design, the waste heat collected from the buildings via the chilled water loop will be captured by new heat recovery chiller and moved to a new hot water loop. The new hot water loop will replace the current steam system for delivering heat to the campus, and it will be more efficient and safer, greatly reducing heat loss through the distribution system. The benefits of SESI are substantial. Due to the significant reuse of heat as well as lower line losses, the new energy system is 70% more efficient than the existing cogeneration process. SESI also provides a significant reduction in campus water use. Since a majority of the waste heat from the chilled water loop is reused instead of being discharged via cooling towers, water use at the central energy facility is cut by 70%, saving 18% of the total campus potable water supply. Replacing Stanford's aging energy system requires a substantial investment regardless of the technology employed. By converting from steam to hot water and using heat recovery, however, SESI provides the university not only a lower initial capital cost than installing a new gas-fired cogeneration system, but also significantly reduces operating cost over the life of the project. Furthermore, since the new plant will be run by electricity as opposed to natural gas, SESI provides diversity in the university's energy supply and the flexibility to readily adapt to future energy technologies. Finally, the campus will reduce its carbon emissions by 50% when SESI begins operation in 2015. This substantial carbon emissions reduction is made possible through the combination of more efficient energy generation equipment, heat recovery to meet the majority of Stanford's heating needs, converting from steam to hot water to reduce heat loss in the campus energy distribution system, and moving from 100% fossil fuel to a diverse energy supply mix, including renewable power sources. The implementation of SESI will require significant work throughout the campus between 2012 and 2015. Over 10 miles of hot water pipe will be installed along with changes to the mechanical rooms of 155 buildings. This work will be carefully sequenced in multiple phases to minimize disruption to campus life. The first phase has recently been completed, and the next phases are preparing to begin in the summer of 2012. Once all phases of the hot water conversion are complete, a full transition from the existing cogeneration plant to the new heat recovery plant will be made, and the cogeneration plant will be decommissioned and removed. Just as Stanford's move to cogeneration 25 years ago represented a major shift in the campus energy technology for the better, the heat recovery plant represents a significant step forward to a more efficient and sustainable technology. SESI is yet another demonstration of Stanford's commitment to sustainability and the university's legacy of adept business investment in research and action. For more information, visit us at sustainable.stanford.edu/climate_action. Thank you.